This problem states, for the element shown on the surface of the circular shaft or beam fixed to a wall with radius c, axial force P, and torque Tap, what is the maximum in-plane shear stress? We already approached this problem looking for the maximum in-plane principal stress. Now we want to find the maximum in-plane shear stress. Once again, we realize that the P is contributing a sigma x stress, and the Tap is going to be contributing a shear stress. And we've drawn it in this direction because that side is essentially moving up more in the same direction as Tap relative to this other side, which is going to be moving, well, or be shifting relatively down. Now, if we look at the element, we can put it out here in another space, right? But it corresponds to this point. We'll go ahead and put an x coming out the same direction as x is here. But we're going to change something up this time. Last time we put y coming out of the top, which was perfectly fine and would still be fine for this example. I just want to show that we can, in fact, pick a different direction for y, and x cross y would lead to a vector coming out at me from the screen instead of, if it were on the top like it was last time, it was going into the screen. Sigma x is in the x direction, and we draw it on both sides. The shear stress is still going up on the left side of the element. It's actually in the minus y direction though, because y is coming down, right? The minus y is going up. And once again, we can draw the rest of the shear stresses, making sure that the heads of these arrows are facing each other. Now, sigma x is still p over pi c squared, and tau xy is still tc over j. But what is the sign of tau xy? From here we see that it's on the positive x face going in the minus y direction, so it means it's going to have a negative value. So when we write the tau xy out, we put a negative sign in front instead of just leaving it positive. The equation we derived for the maximum shear stress is the following. So the square root of quantity sigma x minus sigma y over 2 all squared plus tau xy squared, all under the square root. And once again, we see that sigma y is 0. So that means that this will be 0 here. And we can essentially just plug in what we have for the sigma x, tau xy, and this is going to be the resulting equation that we use. Maybe you want to do it in Python, maybe you want to do it on paper or a calculator. Either way is fine. Notice though, unlike when we did the maximum in-plane principal stresses, what we have here is a equation that only gives us one maximum. Okay. When we were doing principal stresses, you have two. You have a sigma x prime and a sigma y prime, so they're that plus or minus term. And it's just something to note that even though we have the ability to get a negative shear stress, this one's going to give us a positive value, right? As we saw when you have, well, it depends on what values you would have for sigma x relative to tau xy. But you can get into states like in the pure shear case where you go 90 degrees and the shear stress flips. It's not that important here. We're squaring the tau xy and tau xy, well, there's negative or positive. You know, we're going to have a positive plus a positive under the square root. Anyway, thought I'd just add a couple extra tidbits there. I hope you find this video useful. Thank you.